Okay, so we're obviously going to pick up where we left off there earlier this morning. So we were finished up talking about the last sort of equilibrium in this chapter, which is KF. And it is, again, the equilibrium constant for complex ion formation. And the basis of pretty much all complex ions is, as we talked about earlier, you usually have some type of metal. A lot of times it's a transition metal with like a kind of +2, +3, sort of a high positive charge sort of in the center. We have a number of these ligands that are attached to it. As we talked about earlier today, ligands being the Lewis bases, which are electron donors to our sort of deficient metal atom that has a positive charge. And when we do these type of problems, the formation of a complex ion is a lot of times favored. And we know that because if we look at sort of the K values, it is a really large value in a lot of cases. For example, this particular one here we're looking at in this example is 5 times 10 to the 13. Remember, pretty much anything over 1 is considered large. So obviously times 10 to the 13 is a very large value of K. So doing that and looking at sort of the K values, it does affect how we sort of work these complex ion type problems. It's similar, but a little bit different in some of the assumptions that we make when we go through this problem. So let's go through this one here together and sort of talk about those common sort of things that we do when we're dealing with complex ions and KF. First off here, we're going to take 0.2 moles of copper 2 sulfate. We're going to mix it with 1 liter of 1.2 molar ammonia. What is the concentration of the copper 2 ions at equilibrium? A couple of things we're going to sort of assume just in this particular problem, or actually one thing in this particular problem is we're just going to assume that the volume stays at 1 liter for everybody. And that's not always the case, but we'll just assume, just to keep the numbers pretty much where they're at, everything is going to be basically 1 liter. Now, when we mix the copper 2 sulfate and the ammonia together, it is the copper 2 sulfate that is our source of copper 2 ions, right? So that is the source of these copper 2 ions here. And the ammonia obviously is our ligand that's happening here. So that is our ligand that's here is the ammonia as our ligand here. So in this particular case, what we need to get is usually when we do these type of tables is we want to kind of start with the concentration of each of these guys in sort of the mixture together. So in this case, since everything is basically 1 liter, we're going to assume that the moles here of copper 2 sulfate will be the molarity, and we would initially have 0.2 molar. Again, just keeping everything at 1 liter, just keep the numbers the same. Same thing here. Obviously, if we have 1 liter and we keep everything at 1 liter, we're going to have 1.2 molar here of our NH3, and we would initially have 0 here of our complex ion. Now, this is where sort of the first assumption that we make in these type of problems come into play. As we talked about, our K value is relatively large, which means we should really have products there at equilibrium. And although it is a reversible reaction, for the first part of the calculation, we're going to pretty much assume that it's going to kind of 100% go to the product side. So the first sort of assumption is that it is going to go to the product side. And what that means is, since a complex ion is basically made up of a metal in the middle with ligands attached, we are going to assume that because it's going to the products, all of the metal gets used up. And again, you can think about it that you need the metal in the middle, obviously, to make the complex ion. So it is sort of like the limiting reagent. It's going to pretty much get all used up. The ammonia that you add would be like the excess reagent here. You have plenty of it. So normally when we would do a ice table like this is we would use X's. And what I'm going to do then is do that in red, I think. So if we went through here and did our normal change, we would do minus x. This would be minus 4x, and this would be plus x in this particular case. Now, since we are making this assumption here that all of the metals should get used up, we actually know what x is. X will be the molarity of the metal in this case. So typically in these type of tables, we actually don't use x. We actually just use the numbers. So I'll do that one in blue. So this is typically how we would do this type of thing. We would do minus, in this case, 0.2. This would be minus 4 times 0.2. And this would be plus 0.2. Since we already know what x is, that is essentially what we're doing there. So typically we don't use x's in this table because we actually already know what the x is, and we actually just use the actual numbers, but we still need to do everything like we would with the x, again, the coefficient and all that kind of stuff. Any questions on that there? Okay. So again, I just put this x's in here to show you that's sort of the relationship of what we're doing, but we would usually use our numbers. That means that when we do get to equilibrium here, we're going to have 0 of our metal. We will end up with 1.2 minus 4 times 0.2 gives us 0.4, and we end up with 0.2 molar here. First off, any questions? Yes. It's minus 4x. So since we already know what x is 0.2. So we multiply it. So it would be 4 times 0.2, which gives you, what we got there, 0.8. Yeah. So 1.2 minus 0.8.
Okay.
Yeah. Other questions? Okay. So now the problem, though, is really asking what is the concentration of copper 2 at equilibrium? And clearly we zeroed it out here based on our first assumption, and it wouldn't be much of a problem if that's all you needed to write was 0 in this particular case. So there is sort of a second part to the sort of assumptions that we make in this type of problem. The first part, obviously, because of the large K value, all the metal is going to be used up to make that complex ion. The second part of it, though, is it is still a reversible reaction, which means even though almost 100% of the metal gets used up in that complex ion, some of it will come back the other way. Some of it will go back the other way. And the amount that should come back the other way should be a very small amount of the free metal. So those are the two sort of assumptions that we make in these type of problems. First one, all the metal is going to be used up. Second one is, even though technically speaking, almost all of the metal is used up, because it is still a reversible reaction, some of that complex ion will break back apart and will produce a little bit of the free metal in solution. The key is you should definitely end up with a very small amount of free, in this case, copper 2 floating around in that solution. So what we typically do is, even though we sort of zero out our metal here in our first table, what we're going to do now is come back to our table, and we're going to call the copper here X, because that is what we're trying to find. And we could do that by using our KF expression, which is the concentration of our complex ion. Divided by the concentration of copper 2, which is what we're interested in, divided by NH3. And again, we still need to take it to the 4th power there. Putting in our numbers, by the way, that would equal our 5 times 10 to the minus 10 to the 13, actually. So putting in our values, that is 0.2 up on top. That is the concentration of copper 2 on the bottom, and that is 0.4 that we would take to the 4th power. We're going to solve for basically the copper 2 concentration at this point. I'm just going to rewrite it on the next page here, I think. There we go. So basically we have 5.0 times 10 to the 13 equals our 0.2 divided by the copper 2 and our 0.4 to the 4th. We're going to solve it, and when you do solve it, basically these two guys switch places. So these two guys basically end up in opposite places. Divide the 5 times 10 to 13, multiply the copper 2 over to the other side, and when you do that, you get 0.2 divided by 5 times 10 to the 13 times 0.4 to the 4th. And we end up with 0.2 divided by 0.4 to the 4th divided by 5 to 13. Looks like a copper concentration of 1.6 times 10 to the minus 13 would be the concentration of free copper 2 ions at equilibrium. Is that a large number or a small number? Yeah, it is a really small number, and that does validate our second assumption, which is, and our first one as well, which is basically all of the metals going to pretty much be tied up in that complex ion, but a little bit will come back this way, a very, very small amount will come back and still be free in that solution. Almost nothing is pretty much free. Again, that's like 12 zeros and a 1 6. So very, very little of the free ions are floating around. What that does show is, as we talked about, basically the formation of that complex ion is definitely favored. When that ligand gets near that metal, they're going to basically attach to one another and want to form the complex ion. Any questions on that calculation there? Okay, so why don't you try one here? In this case, we're not going to keep the concentration equal or anything like that. So I'm sorry, the volume. So go ahead and see what you come up with. This is a stepwise formation. We got the 2 steps there on the bottom with the K values that go for each step. We're basically looking for the concentration of everybody at equilibrium, silver, our kind of intermediate, our complex ion. If we take 150 milliliters of 1 times 10 to minus 3 molar silver nitrate, and we mix it with 200 milliliters of 5 molar of our sodium thiosulfate there. All right, so give it a try, see what you come up with. Okay, let's take a look, see how you're doing. So obviously we're looking for kind of like everybody's concentration. We do have a stepwise formation that's given to us. If we want to, we could get the overall reaction that's sort of happening by simply just really adding both of these together. The AgS2O3 minus would cancel obviously on both sides. And that would leave us that basically we're taking a silver ion plus a couple of these ligands here. And we're forming our complex ion, which is this guy here. We could also figure out the Kf value if we wanted to. You might not need it, but you could figure it out. Again, we would actually multiply these two numbers together. So if we do that, it looks like we get a 2.9 times 10 to the 13, again, by multiplying those two guys together. First off, any questions on that part of it? We are mixing 2 different solutions here. We're mixing silver nitrate and sodium thiosulfate, and really they're each a source of the things that we need in our overall reaction. Obviously, the silver nitrate is a source of the silver that we need, and the sodium thiosulfate over here is our source of the S2O3 2-. So we can approach this like an ice table like we did in the last one. We do again want really the concentrations of the silver and the S2O3 2- that has been mixed together. So again, we need to do like an M1V1 equals M2V2. To get the concentration of the silver that comes from the silver nitrate, we are using 150 milliliters of it. And the concentration is 1 times 10 to the minus 3. Our total volume is 150 and 200, right? So we're dumping basically 150 plus 200 milliliters together, gives us a total volume of 350 milliliters. So that is actually what we want to divide this guy by, the 350 milliliters. Again, the milliliters will cancel and that'll leave us the molarity. And for our silver here, 150 times 1 exponent minus 3 divided by 350, one more zero, there we go, gives us something like 4.29 times 10 to the minus 4 molar as our sort of opening concentration there for the silver when we mix it together. We could also obviously do the same thing or same type of calculation for our other guy, which is the S2O32 minus in this case. In this case, we're using 200 milliliters of that guy with a concentration of 5 molar and the same total volume when it all goes together for a swim. Once again, the milliliters will cancel, giving us 200 times 5 divided by 350. Looks like a 2.86 molar here. Any questions on that there? So since we can have the overall reaction, we could look at the overall reaction since we actually have both of the reactants there in their sort of mixed form. So rewriting that overall equation of silver plus our couple of these guys here, giving us our final complex ion down there. Initially, we had 4.29 to the minus 4 for our silver, 4.29 times 10 to the minus 4, 2.86 and 0. So our K value, as we can see for this, was to the 13th. So we can make the same assumption here that all of that silver should get used up in this reaction. So again, the change part is actually going to be the amount of silver, 4.29 times 10 to the minus 4. This would be minus 2 times 4.29 times 10 to the minus 4. Again, the 2 is like 2x there, so we got to still have that 2. And this would be plus 4.29 times 10 to the minus 4. That's going to give us at equilibrium 0 for our silver based on our assumption. We'll have 2.86 minus 4 times 4.29 to the minus 4. Gonna basically still have us at like 2.86, and we would have 4.29 times 10 to the minus 4. Any questions off of the first ice table here? Now, from the actual first ice table that we just did, we actually got a couple of answers that we were looking for. From the first ice table, we saw that the S2O32 minus was 2.86 molar, which is the equilibrium line. We also figured out the concentration of our complex ion at equilibrium, which was also our other equilibrium value there, which was 4.29 times 10 to the minus 4. So using that sort of combined table there, our reaction, we were able to actually get like 2 of the things that we're kind of looking for. What we have next, though, is a couple of things that we're still looking for. So at this point, we do obviously have this guy and we have this guy. So there's a couple approaches that you could take at this point. Because they gave it to you in a stepwise fashion here, we could actually go to the second equilibrium step there. And if we look, we have this guy from our first table and we have this guy from our first table. We could use the equilibrium expression and actually figure out that guy's concentration. So that's how I'm going to do it here first. So what I'm going to use is the second step and the K value that goes with just the second step, which is 3.9 to the fourth. And I'm also going to use the equilibrium expression for that guy, which again is for our second step. And that would be our product over our reactant. And again, that comes from not the overall reaction, but actually just the second step here is where that expression, that's why we're not squaring the S2O3 here, because it is not coefficient 2 in the second one. That would equal the K2 value of 3.9 times 10 to the fourth. Again, from the above table, we have both of these concentrations. So that would give us 3.9 times 10 to the fourth is equal to 4.29 times 10 to the minus 4 divided by what we're looking for, which is this guy. And this guy here would be 2.86 there from the above table. Putting those numbers in, again, basically these guys are going to switch places. Gives us that this guy, which is what we're looking for, one of the answers, would equal 4.29 to the minus 4 divided by 3.9 to the fourth divided by 2.86. And again, you basically get 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the fourth and 2.86 here. Gets us, looks like 3.8 times 10 to the minus 9 molar here. If I punch that all in right here, double check. Any questions on that? So that allowed us, by using just the second step there, to figure out the kind of intermediate concentration. Now that we figured that one out, we actually could then go to the first step, and we now have this guy's concentration, which is what we just solved for. We still have the equilibrium concentration of this guy. So we actually can use the very first step there to figure out the concentration of the silver at this point, because we have both of those numbers. So if we did that using the first equation, 7.4 to the 8. That would be this equation, which is the silver plus one of these guys, making our silver S2O3 minus. And again, using the K1, which would be this, divided by the silver, which is what we're interested in, and the S2O3 2 minus. Again, we're using the first step, so there is no squaring, would be 7.4 times 10 to the 8. Solving for silver would be our silver concentration here, divided by 7.4 times 10 to the 8, and our S2O3 2 minus. Putting in our numbers that we have from the previous there, that would be 3.8 to the minus 9 up on top. That would be our K1 value on the bottom. And that would still be our 2.86 that we had at equilibrium there. That gets us, divided by 7.4 exponent 8 divided by 2.86, gets us a 1.8 times 10 to the minus 18 molar, which is the silver concentration at equilibrium. That also validates our assumption, because that is a very small number, which again is what we would assume to happen. So what this shows you is a couple of things. You can use each of the individual steps here because they're all equilibrium steps as long as you have the equilibrium concentrations. And you could kind of go each step backwards and figure out what you were missing. That is one approach that you could do here. Any questions first off on that approach? Now, you may be saying, couldn't we just have kind of used the overall equation and the equilibrium constant that we calculated? And the answer is yes, we could have at this point went into the equilibrium expression for the overall reaction. And if we did that, we would have the KF, which we calculate, I think on the very first page there, which was 2.9 to the 13, would equal our complex ion here, which would be -3, divided by our silver and our S2O3 2 minus, and we would square it. And again, we would square it because of the 2 that is here. So in this case, we're actually using the overall equation and the K value that goes with the overall equation. We could put our numbers in at this point, and we would end up with 4.29 times 10 to the -4 divided by the silver concentration and our 2.86 squared. Rearranging would give our silver concentration is equal to 4.29 times 10 to the -4 divided by our 2.9 times 10 to the 13 times our 2.86 squared, and you should end up with the exact same answer that we got there. So you could have used the overall equation and the KF like we did in the first one to first get the silver concentration. At that point, if you chose to do that route, you then would probably have gone next into the first equation here. Since you would have the silver, you would have this, and that would allow you to solve for that guy as well. So at some point you would need to use obviously the stepwise one here because it has that intermediate that got canceled out. But you could have went silver concentration first and then came back and got the other guy by going through there. Any question on either of those ways there? Okay, so this is complex ions and how we sort of go about them. Let's take a look at one last example here that sort of mixes the two things that we've been talking about here in this chapter. And that is KSP and complex ion formation. So let's take a look at this one here together to see what's going on. So in this particular case, we want to calculate the molar solubility of silver chloride in 1 molar ammonia. And it's basically 2 equilibrium sort of steps that are happening here. We have our KSP step, which is the silver chloride breaks apart into silver ions and chloride ions. And we also have really the complex ion formation, which is the second step that's happening here, the silver ion and the ammonia coming together to make our complex ion. So we could approach the same sort of way. We could add this together to get really the overall reaction that's taking place. And actually, in this particular case, it is actually the silver ion that's going to get canceled out as it's on both sides. That is going to leave us with really what is happening here, which is silver chloride that's in the solid state. You add a little ammonia to it, and it will basically free up the silver and make this complex ion here. And there will still be some chloride floating around. Now, if I want the K value for this guy, can I multiply these two together if one's a KSP and one's a KF? Is that okay? The answer actually is it is okay because they are all equilibrium constants. It doesn't really matter, even though the little letter is different. They're all products over reactants and they're all the same sort of thing. Just like we take, right, KW is equal to KA times KB, not a situation, no problem there. So kind of the same idea here, even though they're kind of 2 different equilibrium constants, they're ultimately still equilibrium constants. So We could actually get the K value for this by multiplying these guys together, which would be 1.6 to the minus 10 times 1.5 to the 7. And that's going to give us a K value here of 2.4 times 10 to the minus 3. And again, we're getting that by multiplying those two together, not adding in this particular case. So when we look at the overall reaction, it is sort of what the question is asking, which is what is the molar solubility basically of silver chloride in ammonia? So although it's kind of two different equilibriums coming here, and we are forming a complex ion, we're looking for the molar solubility. So we will treat this more like a KSP type problem in this case. And because we're looking for the molar solubility, we're going to throw back to our good letter S, right? Which stands for molar solubility, like we did in our KSP type of reactions. So we're going to start with the actual equation here and see what we end up with. So if I rewrite that equation one more time, we have our silver chloride plus our couple of ammonias, making our complex ion here, and our chloride with our K value of 2.4 to the minus 3. So if we look at pretty much what's given to us, the only number that's given to us is we're going to dump 1 molar of basically ammonia in there. So we could start with 1 molar here, and we pretty much have nothing of this guy and nothing of this guy. The change part here is going to be very much like a KSP, except in this case, we actually are going to have somebody on the left-hand side there, which is the ammonia, and it's going to be minus 2s. This would be plus s and plus s here. So a little bit different because we are mixing obviously our KF and KSP together. So we actually, in this case, actually do have something we need to worry about. I am clearly not worried about this guy because it is a solid, right? So I'm not going to put anything there. That means when we do get to equilibrium, we end up with 1 minus 2s here, s and s. Any questions on the ICE table there? Like normal, we're going to really solve for s here. So our equilibrium expression would be our complex ion times our chloride divided by just the ammonia, but we again still need to square it because of the 2 that is there as well. We've got to make sure that we do square it. And that obviously equals our K value there. Putting in our numbers gives us basically s squared up on top, 1.0 minus 2s squared on the bottom equals 2.4 times 10 to the minus 3. So we're going to solve for s here, and to solve for s, it is a perfect square on both sides. So we could do a nice square root action there on both sides. When I do that on the left-hand side, leaves me an s up on top, a 1.0 minus 2s on the bottom. And the thing I always forget to do, which is actually take the square root there of the other side. So we're going to square root the 2.4 to the minus 3. And that gets us something like 0.04899. We're obviously going to multiply this entire thing to the other side. When we do that, we get s is equal to 0.04899 minus 2 times that, which will get us 0.09797s. Obviously combining our s's to the other side, so we're going to bring this guy back this way. And that's basically 1 plus that, right? So that gives us something like 1.09797s equals 0.04899. Dividing it to the other side gets us 0.089 moles per liter, would be the solubility of silver chloride. Again, it's a one-to-one relationship back to this guy in ammonia. So if we take that and times it by, what was that, 107.9 for silver plus 35.45 there for chlorine, that is approximately about 12.8 grams per liter of silver chloride you could get to dissolve in ammonia. First off, any questions on that calculation there? Multiply by the molar mass, obviously, of silver chloride there at the end. Now, if you remember, I think we did silver chloride earlier on. And just for reference point of view, if you solve for silver chloride in water, we had our silver like we had earlier on in that slide. That had us with 0, 0, right? Changes plus S, gives us S and S, gives us S squared was equal to our KSP there, which was 1.6 to the minus 10. Gives us an S of 1.3 times 10 to the minus 5 moles per liter, which if we times it by the molar mass of silver chloride was like 1.8 times 10 to the minus 3 grams per liter, are basically 0.0018 grams per liter in water. That is the solubility of silver chloride in water, like we calculated, I think, earlier on in this chapter. The solubility of it in ammonia is 12.8 grams per liter. Which one is it more soluble in? It is much, much more soluble in ammonia than it is in water, right? Way more soluble, right? than it is in, you get about 12 grams or 13 grams per liter versus like 0.002 grams per liter. That's a very big difference in solubility. What that emphasizes is the presence of a ligand and the need to form a complex ion is very much favored. And that's why we see very large values for KF, because it is a very strong attraction. This is actually something that you do in those qualitative analysis experiments I was talking about earlier. You make silver chloride to prove that you had silver chloride, and it is in a solid version. And what you end up doing is actually adding some ammonia to it. What that does is it frees up the silver into that complex ion. And what you end up with is now the silver floating around in the solution. So the solid actually disappears. It's such favored that that complex ion wants to form that if you put that ligand in with some solid silver chloride, the silver will jump out of the solid, go into forming that complex ion and go into solution. This guy is aqueous, which means it's floating around. The other second part of that is you then put a lot of acid in it. When you put a lot of acid, you get rid of the ammonia, makes the silver still there. And then there's also chloride still in this reaction. So you can reform the silver chloride coming back. And that's what is the positive test, for example, for silver, is to make the solid, make it go away and then make it come back, is actually a positive test for silver. Question on this problem here. Okay. So that is chapter 15. Yes. So we are off to, I think it's 16, I think. Maybe it's 17. I think it's 16 though in your book. We're going to talk about in this chapter thermodynamics. So the good news is we have now just descended from our roller coaster to the bottom of the tough stuff in terms of the hill. So again, like I said, 14 and 15 was pretty much the peak of conceptual information and stuff like that. We're going to talk a little bit more about some stuff where, you know, you kind of pick some formulas and plug and chug type of thing. You still obviously need to know what's sort of going on, but maybe it's not as much of the conceptual aspect of it. So once again, this would be more exam 3 stuff. Obviously, we are starting here. So entropy, free energy and equilibrium. I'll spit that out. So in this chapter, we're going to talk about some other letters of the alphabet, which is nice. We're going to revisit our good friend delta H, which is enthalpy, right? Enthalpy is basically the heat of a reaction. And as you should probably know, we talked about, right, delta H is negative, is an exothermic reaction, which means heat and energy is going to be released. If obviously the delta H is a positive number, it would be an endothermic reaction, which means heat and energy is being absorbed. We're going to add to that some of these other guys here. We will have delta S, which is the entropy, and we'll talk about what that is in just a second, not to be confused with enthalpy. Gibbs free energy is delta G, that is free energy. And of course, what would a chapter be without coming back to our favorite letter of all, which is K, which is equilibrium here. So we will get back and sort of tie these guys into the equilibrium sort of reaction or expression as well. So we're kind of talking about in this chapter really thermodynamics, and you kind of talked about thermodynamics in Chem 50 when you did all the delta H's and the enthalpy. That's sort of the first law of thermodynamics, which is sort of the conservation of energy. So let's talk a little bit about the idea of processes. And first off, a lot of what we look at in this particular chapter deals with the idea of not whether how fast or slow a reaction takes place, but whether or not a reaction is spontaneous. And as we talked about, I think when we were talking about kinetics earlier on, when we talk about a reaction being spontaneous, it doesn't necessarily mean that it occurs really fast. You could have a spontaneous reaction that occurs really fast. You could have a spontaneous reaction that occurs super slow as well. It just means that if a reaction is spontaneous, what that means is under those particular conditions, you would expect this reaction to actually take place. Be it fast or be it slow, it is the right conditions for that reaction actually to take place. Obviously, like we talked about in kinetics, that is really what deals with how fast or slow a reaction happens. But thermodynamics really deals with that idea of spontaneity. So it's a very common thing that people have in their head. They think spontaneous and they think, well, snap your fingers, it happens like really fast. But again, that is exactly what we're not really talking about here. These are all spontaneous processes. Waterfall runs downhill. Hopefully water goes down. We have sugar. You put it into a cup of coffee, it would melt at 0 degrees and 1 atmosphere. We do have water that freezes and also melts depending on which way you're going with the energy. When we talk about heat and energy, things do flow from hotter to cold, right? The hotter guy gets colder, the colder guy warms up, and that's a result of the hotter guy transferring his heat to the colder guy. Warms up the colder guy, lowers the temperature and cools down the guy that's a lot hotter. If we have iron that's exposed to oxygen, that is a spontaneous process. Basically need some iron, some oxygen, a little bit of moisture, and you're pretty much good to go. They say skiing downhill is spontaneous, right? And probably what you don't want to see if you're going downhill is this person coming up the hill there. That is a non-spontaneous process. You got to do some type of work, right, to get yourself up the hill. Down the hill, you just hang on and hope for everything goes out okay, and you avoid all the trees, right? So this is also a spontaneous process up on top. And if we have some gas molecules separated in a chamber by obviously a valve, if we open up this valve, you know, spontaneously those gas molecules are going to migrate over to the other side. In a non-spontaneous process, if we had gas molecules on both sides, they probably wouldn't spontaneously all decide to go that way. You could sort of help them out, maybe by heating this side or something and kind of move them off into that direction. But just spontaneously, it's not going to just happen that they're all going to kind of go over to the other side. So when we think about reactions and we think about things sort of happening spontaneously, we sometimes think about it in terms of, you know, if it's an exothermic reaction, we would expect maybe the reaction to occur spontaneously. And maybe if it's an endothermic reaction, maybe not so much occurs spontaneously. So what we see here are all spontaneous reactions. That's a combustion reaction, which has a delta H of negative, which means this is exothermic. We also have the formation of water, which overall is a negative delta H, which is exothermic. We have the melting of ice, which is this guy, which is obviously endothermic. And we have the dissolving of a ionic solid in water, also endothermic here. So all these things do occur naturally and spontaneously, right? If we took an ice cube out, you don't have to do a lot to it, right? It is going to just kind of naturally pick up the energy from the air, and it's going to start to melt. So the idea of delta H or enthalpy being really the overwhelmingly sort of thing that we should look at doesn't necessarily hold true because as we can see from this kind of simple example here, we have exothermic reactions, which are spontaneous, and we also have endothermic reactions that can be spontaneous as well. Although exothermic reactions, do sort of favor spontaneity, because if you just think about it logically, exothermic, you're releasing energy, you got a lot of energy sort of happening. So that helps things sort of occur and sort of happen, right? When reactions take place, right, you need a certain amount of energy to get up and over the hill to the other side. So if you have sort of an exothermic one, you got some of that excess energy to sort of do that. So what we have to look at is maybe another value or factor that can help us decide whether or not a reaction will be sort of spontaneous or not. And one thing that we could look at is what is known as the entropy, which is abbreviated with an S. A lot of times what we look at is delta S, which is the change in entropy. And the entropy is the amount of randomness or disorder there is in a system. And again, when we talk about thermodynamics, we usually talk about two things, the system and the surroundings, right? The system is pretty much anything that you're working on. So if you're working in a beaker or something like that, your system's your beaker. The surroundings is pretty much everything outside of that beaker. And a lot of times when we talk about sort of energy flows, from the system to the surroundings or the surroundings to the system. And when we look at the randomness or disorder of a system, as the order increases, we actually see a decrease in the entropy. And something that's a little bit different is when you get sort of a negative value for entropy, it's actually when we have a lot more order happening. So a lot more order will result in a negative value when you do your delta S. Delta S is kind of like a state function, final minus initial state, like we talked about. And if you end up with a lot more order than what you started with, you will actually end up with a delta S that is more negative. And that's different than if you have a situation where you increase the disorder. So things start going crazy, a lot more things are happening. If you increase the disorder, the delta S actually becomes more positive. So sometimes we think about negative as, things happening and stuff like that. But delta S is a little bit opposite of that. The more positive the delta S is, the more disorder that you have happening in that situation. Very common, sort of easy way to think about disorder is looking at changes of state. So as you go from solid, right, things in their solid state are pretty ordered. When you go to the liquid state, things have a little bit more energy, things are moving around. Why liquids are fluid, right? They have enough to kind of pass one another. So we're creating a lot more disorder. And then obviously when you get to the gas phase, everybody is moving around, flying around. There's a lot of things moving and stuff like that. So a lot more disorder. So the delta S in gas is a lot more positive than the delta S in the liquid, and the delta S in the solid would be a lot more negative than any of those guys there. So when we look at an equation such as this one, which is basically solid going to liquid, or ice going to liquid water here, we would expect the delta S actually to be more positive. Again, we're going from solid, which is a more ordered state, to liquid where there's a lot more disorder, things moving around, and we would expect the delta S value here to be more positive. I would recommend thinking about it one of two ways, either order or disorder. So sometimes people confuse themselves thinking disorder and order. So, you know, either the disorder is increasing or the disorder is decreasing, and vice versa for the order. So you don't hopefully confuse yourself. Disorder is related to probability. And when we talk about probability, a probable event is one that can happen in many ways. An improbable event is one that could only happen in one of only a few ways that could occur. So obviously, if we needed to get out of a room and there was multiple doors, it's probably pretty probable if you needed to get out of the room, you could just pop the door open and leave, right? So it's a very easy way to do that. If you know, it was a room and there was no doors, just a very small window at the very top of the wall there, you know, that's a very difficult way to get out of the room. It's probably a little bit more improbable that an event will occur. So sort of in life, there's a much more probable chance that you will screw something up, yes, and do something wrong. So, you know, there's a very high entropy because, you know, there's a good chance of kind of screwing something up. In a ordered state, doing something correct all the time, right? There's one or few ways of doing that. So in an ordered state, there's a very low probability of occurring, and we have a very small entropy. A disordered state, a good chance of messing things up, has a very high probability and a large entropy that happens. So there is a sort of relationship between entropy and what is sort of referred to as probability and what is referred to as microstates. And that is what the W stands for here. That is what is known as Boltzmann's constant, which is down here. So the entropy is equal to Boltzmann's constant times the natural log of W. Microstates you could kind of think of as the different ways you could accomplish something. So if we have 4 circles and we wanted to put the 4 circles either on one side or the other, there's pretty much only one way you could do that. You put it on the left side or you put it on the right side, basically, which is the same thing. If we wanted 3 circles in one and one in the other, there's 4 different ways of doing that. And if we want to go and go 2 circles on each side, there are 6 different ways of doing that. There is a lot more ways of doing the 2 and 2 versus I want to get them all there on one side, right? And there's only one way. Mathematically, if we just look at this equation, which is the entropy is Boltzmann's constant times the natural log of 1, natural log of 1 is equal to 0, right? So we get a very small entropy in that case because we only have one way of doing it, as opposed to if you took S is equal to K times the natural log of 6. You take the natural log of 6 on your calculator and times it by Boltzmann's constant. Natural log of 6 is like 1.79. Times it by Boltzmann constant, obviously you get a much larger value than 0 in terms of you know, the entropy. So the more ways that you could do something, the more probability that that's going to happen, and we get a sort of a larger entropy value than obviously if there's just one way of doing that. So if the number of microstates is greater than what you started with, then the entropy will be more positive, and obviously if it lowers, it will be more negative in that particular case. Any questions on that there? And these are all processes where we do see an increase in the entropy, again, melting, which is the first process. Again, just from the picture, you can see a lot more disorder happening. Obviously, evaporation to our gas phase, again, a lot more energy and stuff happening. When we make a solution, which is a solute and a solvent, before we do that, something like water, which is a solvent, they're all nicely hydrogen bonded together, right, in a nicely ordered fashion. Something like sodium chloride, which is a solid, is together in like a lattice, right? And the positive, negative charge ions are nicely ordered. They have long range order and the patterns repeat. Perhaps you remember, like you talked about, unit cells, cubic unit cells, simple cubic. Anyone? No? They don't teach that in Chem 50 anymore. So, you know, when you talked about solids and sort of the orders and all that kind of stuff, But what happens obviously when you make a solution is you're breaking apart all the ionic solid, and all the water guys got to break apart to accept all those ions and surround all those ions. So obviously you're causing a lot more disorder. Obviously as well, if you increase the temperature, right, you light a match under somebody, they move a lot faster. So things start moving a lot faster, especially gases and stuff like that when you increase the temperature. So you cause a lot more disorder with things flying around and stuff like that. Any questions on that there? All right, I think that's enough torture for today. Have a good one. And again,